Today I'm going to show you how to identify and deal with water recirculation in production logging interpretations. As we can see in this spinner, there are a number of very clear inflow zones, okay? This one being the most prolific. But as we go deeper, we can see that the deepest perforation was not logged through, and if we maximize this track, we will see that the up and down passes are not symmetrical, okay, but they are all shifted to the left to more negative RPS. As the cable speeds are symmetrical, this is a clear indication of downwards flow. Let's have a look at the calibration cross plot now, where we can see that the deepest inflow zone has both intersects on the positive cable speed side. Again, this indicates negative flow. So let's set the thresholds in this case from the distance divided by 2. And we are ready to compute the apparent velocity, in this case using all the passes. So this is the apparent velocity, which again shows negative velocities across the 3 deepest perforations. So this is a producer well, an oil producer. And there are 2 possible causes for negative velocities. One is recirculation, in this case water recirculation, and the second possible cause is actual cross flow. So we need to distinguish between the 2, right? So let's have a look. Let's go straight to compute the rates. I'm going to click here, single phase, oil, and then let's accept the defaults. And let's see how the profile looks like. There we go. So this is our cumulative QZT, and the contributions shows a negative contribution for the deepest perforation. So how do we call this? When a zone is injecting and all the other zones are producing, this is our thief zone, okay? So this is showing a downwards cross flow from these other perforations to the deepest. Okay, is this real? Is this a consequence of water recirculation? Let's have a look. So the first thing is that this well is 50-something degree deviated, so it's an ideal case for water recirculation, especially in the low velocity intervals as the deepest perforations. The other situation that we need to look for is multi-phase conditions. So we don't have a density, but we have a pressure. And if we have a pressure, we have a free pseudo-density. So by clicking here on derivative, I'm going to select all the passes, apply smoothing, and we are computing the DPD set and the DPD set corrected for deviation, okay? And we can start to see that there are different densities, right? Let me just look at the corrected for deviation, and the density down here is around 1.01. So indeed the 3 perforations are immersed in water. The other important thing we need to consider is the dynamic behavior of the reservoir. If we have a look, here we also have a shut-in survey, which indicates cross flow, but in these 2 upper perforations, but no fluid movement down here, right? So the rates are 0. So is it possible to have an injection during a flowing condition, but no injection during the shut-in? Well, let's have a look. If we set some reservoir zones, for example, I'm going to do one for this deepest perforation, and let's compare it to the reservoir zones for the upper 2 perforations, right? We can go to the special tab and look at the SIP, which shows the IPR plots for each of the reservoir zones. So can you see the upper one here in purple and the second one in green are very typical, showing that as the drawdown increases, the rate also increases. But if we now look at the deepest reservoir zone, this one in blue, it shows that as the drawdown increases, right, as we drop the pressure, the rates are getting more negative, right? So this suggests a negative productivity index. Can you imagine like a negative permeability? This is not physically possible, okay? So this is a very good indication that this cross-flow is not real, and we should give it a go to the water recirculation possibility. So let's click OK. To do an interpretation with recirculation, we need to come here to the information reference channels and add a fluid identification tool. In this case, the only one we have is the pseudo density. Okay, so I'm adding this one. Also, water recirculation requires activating the water from the PVT and make sure that you're using the correct salinity. Okay. And that's it. So let's have a look now. I'm going to click on rates, and now Emeraude suggests a water hydrocarbon model with a multi-phase correlation. We go to the rates, rate calculation tab, and for example, if we look at the rate calculation zones down here on, across the negative velocities, we see the negative rate. So let's accept this scenario first, click OK. And we compute this QZT and QZI. Again, we have a thief zone. Now, as we have added the density, we have multi-phase cross-flow, right? But we know that this is not the real situation, right? This negative rate here is due to water recirculation. So what can we do with this? We are going to click rates. And here we need to identify the rate calculation zone that is suffering or is experiencing water recirculation. So in this case, it's the second from the bottom. Okay, we come here, we see the negative velocity, and this negative velocity, we know that this is due to the water going down as the oil is flowing on the high side of the cross section. So we are going to tick this ADF, apparent downflow box. Okay, can you see now that the measured velocity remains negative, but the calculated becomes positive, right? So what is Emeraude doing? Well, it's ignoring the spinner completely. The spinner cannot be used, right? And is using a multi-phase flow correlation to compute the slippage velocity, and assuming that the water is not moving, is calculating the light phase velocity, okay? We need to repeat this operation for all the zones with ADF. So the following zone, the third, is also showing negative velocity due to water recirculation. We click here ADF, and now we are ready to compute the profile. And as you can see now, this deepest inflow zone that was showing a negative contribution now is positive. The spinner here in red, the spinner apparent velocity is ignored, and the calculated apparent velocity, as I mentioned, uses a multi-phase flow correlation. Okay, another option to deal with water recirculation is to use temperature modeling. I've done it in a separate video, so I will add the link to that video in the comments. Okay, hope this was helpful, and see you in the next video.